Hello, my name's Oscar, and today I'm going to show you how to use the Netcode for GameObjects Performance Toolkit from the Asset Store. So the aim of this is to let you understand what you're actually sending over the network and to help you to optimize what you're sending over the network and use less data. This can help you to have more things going on in your multiplayer game, sending more messages, or to optimize it for lower end networks or mobile networks and things like that as well. So this comes in two parts. So the first part is the Netcode profiler. This really helps you to analyze what you're sending, how often, and which parts of your code are eating up all of the network usage. This is similar to the Unity profiler, but it's specifically for everything that you're serializing over Netcode for GameObjects. Once you've used the Netcode profiler to understand where your network usage is being spent, there's the second part, which is the Netcode types. And these are optimized types that let you send similar data, but with fewer bytes. You can see here it says quaternion netcode Euler byte 4. So for instance, this is rather than sending the full precision rotation over the network, which would be 16 bytes, we're sending it with just 4 bytes here with slightly reduced precision. Well, quite a lot reduced precision. But for a lot of things, that's all you actually need. So I'm going to take you through how to use both of these things, the Netcode profiler and also the Netcode types, to really drastically reduce your network usage and get some more things going on in your game. So I've got a very basic setup here using Netcode for GameObjects with the UNet transport. And this is using parallel sync to have 2 copies of the same project. I'll put a link in the description about how to get that set up. And also, this kind of assumes that you've already got something set up with Netcode for GameObjects. If not, then you can use the sample scene that's provided in the asset, or I'll put a link in the description to a good tutorial on how to get started with Netcode for GameObjects. Okay, so when I hit play here on both of the editors, I'm going to host on the left and client on the right. And we've just got a pose sync here going on. And this is a custom script that does the pose syncing. This is the one here. And that's our script that we're going to look at optimizing. So the first thing we want to know is how much data are we using right now? So we can open Window, Netcode Optimization Toolkit, Netcode Serialization Profiler. And straight away, it's not coming up with anything. And this is because we haven't actually recorded any samples of the data that we're serializing. So there's a few different ways to record samples, and I can show you those now. Okay, so this is our very simple pose sync script, which we want to profile with the Netcode profiler. It's a network behavior, and it's got a network object on the same game object. We're using 3 network variables here to set the pose over the network. So this is position, rotation, and local scale. If you haven't read up before on the network variables and the network behavior, I'll put a link in the description to a good tutorial for that. But really, this is already syncing the position. I'll just take you very quickly through what it's doing. Every network tick, if we're the owner of the object, we update the owner. So we're setting the position into our network variables here, position, rotation, local scale. We're setting the network variable. And then if we're not the owner, so we're the follower, I'm calling it, you are setting your own position based on the network variable. So the owner is writing to it, the follower is reading from it. And then we've got some stuff for spawning and despawning as well. But let's not worry about that. So we want this to take samples for the network profiler. The easiest way to do this is to use our network types. So we can go using static into network performance tools types. Okay, and then here we can just swap the vector3 quaternion and other vector3 for vector3 netcode, quaternion netcode, and another vector3 netcode. And what this does is it wraps the type in a way that when it's serialized, it also samples it. And the one thing extra we have to do here is to wrap it in that type. So that has to be a new vector3 netcode, and it's happy with that. I actually like to just do this, which is just say new, and that way when we change the type later to optimize it, we don't have to change this again. So we can just say type, whoops, can't type today, And then here, because it's wrapped again, this value is our actual netcode type, but then that has its own value as well. So we just go value, and then we only have to do this first time we set it up. Okay, that should work, and we should start getting samples. So we can go back to Unity, make sure it's all compiling. Okay, so it's all compiled. We don't have any samples recorded, but we can record some now by pressing play. If we go host and client, then the host has these. So under write and then netcode type structs, we've got a vector3 netcode and we've got quaternion netcode. And how many calls have we had? We've had 2 calls to vector3 netcode, so that's position and local scale, and we've had 1 to quaternion netcode, which is rotation. So it's only actually sent it because of using the network variables. It's only sent it the first time because it knows that it doesn't need to sync it when it hasn't changed. If I rotate, and also we can see the number of bytes here. So we've got 12 bytes per vector3, so that's 3 lots of 4 bytes for 3 floats, and this one is 4 lots of 4 bytes, 16 for 4 floats for the quaternion, X, Y, Z, W. So if I start rotating this now, we should see that going up. We're sending more and more samples, we're using more and more data. Our bits per second is going up, bytes per second is going up, and our number of calls going up, and so on. So 99% of it is the quaternion now, because we've just been rotating this. We could also move this, and then our vector3s go up, and we could do some scaling as well, which would just be some more vector3s. Okay, so all of this is great if we want to only use network variables, but that is not the only way to send data in Netcode for GameObjects. The other way to send it is via RPC calls. So I hear you asking, how do I record samples for the profiler for my RPC calls? So we can take a look at that now as well. Okay, so we're looking at another script now, another example. This one is a serialization example for just sending data to clients over RPC. So this is another network behavior, and we're also using another network object on this. So just periodically, every second, we're sending a color to the client over an RPC. And that RPC is down here. We're not doing anything exciting when we get it. I'll leave that to you. However, as we're sending this just as a color, we won't see any samples for the network profiler yet. So we can make a change to that again. So we can say using static, using network types up here, and then we can just replace this color with a color netcode. And again up here we can just do new color netcode. Again using just new, so that when we change that for something a bit more optimal, we won't have to change that again. And let's have a look to see what that's done. Okay, so we'll connect the host, connect the client, and we can see here that we're both reading and writing. So we have our vector3 and our quaternion from before, but we've also got color netcode here now. So that's what we were sending before. It's a whole 16 bytes just for a color. And in here we've got the actual serialization of the color. We're also reading now, because the way it works in Netcode for GameObjects, when you send something over RPC, you're also serializing it and deserializing it to yourself. So we can also see that that's happening. And if you were running this on a client, which we can also do, you would see that this stuff comes up for the client too. So let's just swap this around, be the client on the left this time, and all read, no write now. So you can see what's going on there. Okay, so we're back in our script here, and the last thing we want to look at profiling is a custom struct. So we've got also an RPC here where we're sending our example object, example struct, and we're just filling that with some dummy data. Again, we're not doing anything with it, but we've got a custom network serialize function here. So it's going to serialize all of those things to the network. So how do we take a sample for this custom struct? The way we do that is we say netcode profiler and we need a reference here. So we've just added using Unity netcode performance tools. Netcode profiler begin sample, and this follows the way that the Unity profiler works, and you can take samples. And we need a reference to the serializer. And we can have a name for this sample. So this is example object. So we begin the sample here, then we serialize the data, and then we need to end the sample as well. So we say netcode profiler, end sample, give it the type and the serializer as well. Okay, so let's jump back and see if that turns up. Okay, so we've got here now we've got our example object, both reading and writing from it. And we can see that that's 44 bytes, which makes sense, right? Because we've got a color, position, and rotation. So that's 16 bytes for the color, 16 bytes for the rotation, and 12 bytes for the position. How can we check that? If we want to go into a little bit more detail, we can have nested samples, and I'll just show you that quickly before we can start our actual optimization to reduce the amount of data that we're sending. So if we want to add another sample just to check that things are what we think they are, we could say within this example object sample, we can add another sample, which is going to be position, and let's call it that. And then we can end, don't forget to end the sample as well. So we're saying begin the sample, example object. Within that, we're having another sample, position, serialize the position, end that sample, and then serialize the other stuff. Okay, so now you can see example object. Within it, it has position, and you can add as many of these sub samples as you like, and we can see that that position is 12 bytes to be expected. So now we know what we're sending. We want to look at how to reduce that data. So how can we send this position, or something that represents our position, with less data? How can we send a color with less data? This is covered within the netcode types, so we can take a look at that now. So we're back to post-sync here, and we're looking at our network variables. We're thinking, how do we reduce this? So a very obvious one for me would be that this position, it might be quite a small game. Maybe we don't need to go to have such a huge range of values or such high precision as a float. So we could swap this for a vector3 netcode half, which would, let's see, so this says it's 2 times data saving, 6 bytes instead of 12 bytes, and we're using halves for each dimension instead of, for each component, instead of full floats. Quaternion, we've got actually quite a few options. We've got the halves, which would be the most obvious one, so we store each component as half. We've also got each Euler component as a U-short, and all of these say the data saving and also the precision here. And then we've got byte 3 and byte 4. So I quite like byte 4 because that gives us like a nice balance of like a quarter of the data used, but still we've got like 0.35 degree precision, which unless it's a huge object, you're not really going to notice that. So let's say use the Euler byte here. And for the local scale, we can just have half as well. And we can go back and take a look at see what that's done to our network usage. Okay, we're back and we can see our netcode structs. So now we can see we're using our netcode half types and we're using our netcode Euler byte 4 types. So we can see the data here. So half, we're using half the data. It was 12, now it's 6 bytes. And here we were using 16 bytes and now we're using 4. So that's quite a big data saving. If we're sending that on update or something like that, we've just cut our positions and local scales in half, and we've cut our rotations in a quarter. So we can rotate it around and we're sending far less data than before, and this will be helping the stability of our game. Right, let's optimize the rest of it. Okay, so we're back in our network serialization example to look at the RPCs that we're sending and how to optimize those. Right now we're sending a color every so often, and we're using just the default color type, so it's 16 bytes. It's pretty big for a color. So what we can do is we can say, let's use byte 4 clamped. So this would just be sending 1 byte per channel, or this one was 1 byte per channel, but we'll actually skip the alpha channel. It might be that it's just sending the emission color of something or the albedo. So this should be a big data saving. So this is a 5.33 times data saving. That's our biggest yet. So let's go and see what that's done. Okay, so we're running now and we can see we've got a color netcode byte 3 RGB clamped here, and that is sending just 3 bytes for RG and B. And we can actually go into that and see that we've got each one is sending as 1 byte So we've got 3 times as many calls on that one, and you can kind of understand how that's being sent. But what about our custom struct, the last piece of the puzzle? Okay, so we've got our custom struct here, and I'm just going to remove the position subsample because I think it makes this a little bit simpler. Okay, so we're going to replace this with just serialize vector3, and this is coming from the netcode types. We need to give it the type of this example object, and we also need to tell it that this is the serializer. And then we can do the same thing with our quaternion and color here. So serialize quaternion and serializer, and we can do serialize color, and it's serializer. There was another part to this, which is that we weren't actually able to serialize our GUID before because that wasn't something that is sort of supported by the serializer, but now we can say serialize GUID, and we can say serializer ref GUID. Oh no, ID it's called. Great. Okay, so now we're actually serializing these with our serialization functions, which we can optimize pretty easily. Let's go back and see what this looks like. Okay, now within our example object, we can actually see that we've got serialized GUID, serialized quaternion, color, and vector3, and we can see the individual sizes of those. And now we can go and optimize those by just changing how we're doing that. Okay, so we can go into the vector3, and we've got, again, a few different options. These are actually pretty much the same options as we did for the structs, but we're going to do our vector3 as a half, and we're going to do our quaternion as an Euler byte 4, and we can do our color as a RGB. Let's do 4 this time. Maybe there's some alpha in here this time. Okay, so now we've slashed it. Right, we're using half the data for our vector3, and again we can see that that's doing 3 lots of each dimension. Each one is 2 bytes, and we're doing quaternion as Euler byte 4, and we're doing serialized color as byte 4 clamped, and again you can see that there's 4 lots of that that same function call in there. Okay, so what we've done here is we've managed to see all of our network usage, and we can see what we're reading, what we're writing, and we've also managed to reduce it. And as you can see, I haven't actually shown you here, but hopefully this will rotate, and you can see it's pretty much the same. As you rotate one, the other rotates. We can still move the position. The precision is reduced, but this is pretty likely that you won't notice that, and you can have a play around with the different types to get the right balance of data usage and also precision. And I'll just show you a couple more things that will help with that, which is, first of all, we've got the documentation here. So you can open that. If you also use Visual Studio Code, you can do Control-Shift-V, and that will open up the reader view. And we can have a look. And we've got getting started, feeding the profiler, that was the first thing we covered. And then we've got measuring your serialization, blah, blah, blah. We've got all of the different types in here as well. So we've got all of the bools. Oh, I didn't cover the bools. The bools are the best bit. Maybe I'll show you the bools in a second. So we've got the bools, we've got the ints, floats, vectors, vector2, color, quaternion, and GUID. And we've got the same thing for the serialization functions. These are pretty much the same, but these ones are for just using the types, and these are for using the serialization functions. Okay, I'm just going to go back and show you the bools here, because I think that's an important thing to have. So let's say we've got a number of bools in our example object, like we can have a bool is active, a bool is alive, I don't know, has magic or something. Maybe we could have a load of these. Has ammo, some sort of magic thing with guns, and you want to serialize all of these. But actually, the way that you would do this normally is you'd have to serialize all of them, and Unity takes each bool, which is really just one bit, 0 or 1, and serializes it as a whole byte for that. So these 4 would be individual bytes, and actually we could have more of them if we can come up with some other silly names. So as has health, I don't know, is crouching, and go on one more, and is a potato. Okay, so we've got a load of these. So this would normally be 1, 2, 3, 4, 5, 6, 7 bytes for that. We can reduce that again, I mean, kind of before we've even created our problem here, but we can send that with much less data. So what you would normally do is you'd say serializer, serialize value, and then you would go ref is active, and then that's 1 byte, and then another byte, and so on until we're sending 7 bytes. But instead, what we can do is we can say serialize bool 8 as byte, bools 8 as byte. So what we're saying is we're taking 8 bools and we're going to serialize them all as 1 byte. So each one of these bools will be a bit in that byte, and that way we won't send 8 of them, 8 bytes. So let's say ref is active, ref is alive, has magic, and so on and so forth. So we've actually got 7 here. This needs 8 because there are 8 bits in a byte. So we can just send the last one twice. And actually, it's always the minimum amount that it can send anyway is 1 byte. So you're not wasting any data here by sending it twice. And it's happy with that, except no, it's not. Oh, we didn't give it the serializer. Okay, so serializer, and then all of that stuff. Okay, so here we can see our bools 8. Serialized bools 8, that's just 1 byte, and we're sending 8 different bools within that byte, so that's pretty optimal. You can't really reduce the data for 8 bools more than that. That's probably the biggest data saving that we have in there. So yeah, that is an 8 times data saving, so that's pretty good. Okay, so the last thing I'll show you is just how to evaluate the precision of these different reduced data types, and I've got an example here which is in the examples folder, just in that sample scene, and you can have a look at the variable test. So this actually uses every single one of the types that can be serialized and shows the data that we're syncing. So here we've got network variable test on both of them. So this one is just a standard bool sending with a whole byte, so we can see that synchronized. I'll turn that on and off. And then these ones, bool byte 0, 1, 2, 3, 7, these are our bool byte 8 thing, where we've got 8 bools in a byte, and we can see each one of those if you turn them on and off. So this is kind of just a test that that's working. And if we were to have a look at our profiler, we'd also see these turning up. Here we are. We've done one call to that, but as we do this, that'll go up, and we can see that each one of those is still just 1 byte. Similarly, we can see with our ints, this one's an int, just a standard int. This will go right up all the way to some huge value, which I can't remember what the max is, but I know it's above 65,000. So let's say 120,000. And we're still syncing there. So this one is a U-short version where we're sending it as half of an int's precision, and it's also unsigned. This is just for an index or something like that, and it'll get right the way up to 65,000, and then it starts to wrap back around again, as you can see there. So on the left, we've got the value that we're sending, and on the right, we've got the value that we've received and interpreted. So up to this point, it's okay, and then beyond that, that's a problem. So you can use this if you're using a value that's under 65,000. If you're over that, you can use an int. Here we've got a byte, so similar kind of thing, but only up to 255. So if you just got an index of a small number of things, then you can use this up to that point. It's fine, and then beyond that, it'll start to wrap again, as you can see here. So we're wrapping around. But yeah, up to 255, completely fine. Over here we've got floats. That sends it exactly as it is. I mean, you're getting the idea here, which is that on the left we've got the value, and on the right we've got the value that you receive, and you can kind of just get an idea of the precision here. So, for example, our rotation here is the values aren't going to be exactly the same. So actually, float's a good example. So if we were to have a half precision float, we've got 9.27. But over here we see 9.27 something, and that is because the precision is reduced. And if we have it as a byte clamped to 0 to 1, that precision is reduced again. But again, less data, less precision. It's up to you to decide what works with your game. Same kind of thing over here. This one is clamped, so it doesn't go above 1. And you can just get an idea of how all those work. This is all in the documentation as well. But yeah, worth having a play with. Here we've got our RGB3 value. So we can make that red and it will become red, but if we change the alpha doesn't change. This is just 3 RGB only one, whereas over here the alpha would change, as you can see on the right there. Alright, so I think you got the gist of that. Okay, so I hope that was really useful for you. This has given you an overview of how to get started with the Netcode performance tools. And if you've got any questions, just put them in the comments. Useful to have some likes and things for this. But yeah, any other content you want me to cover, definitely ask about that. And I hope you're all reducing your network usage, and you've got now you have super stable multiplayer games, and you have hundreds of different objects all going around with physics and all of that, and all with optimal performance. So yeah, thanks for watching. Bye bye.